다시 커졌네요. 네, 이렇게 이게 첫 번째 강연인 줄 제가 몰랐습니다. 제가 이제 바로 옆에 있어서 빨리 하고 이제 치우자 해서 좀 3월 9일 날로 이제 날짜를 잡았습니다. 그래서, 소개를 잘 해주셔서 정말 감사드리고요. 저는 바로 옆에 이제 걸어서 한 30분, 20분 거리에 있는데, 제가 가끔씩 여기에도 이제 오고 그럽니다. 네. 그래서 이제 오늘 제가 이제 여러분한테 이제 이렇게 발표할 내용은, 그러니까 최근에 이제 액정에 관한 수학적 이론이 있는데, 이제 거기에 대해서 될 수 있으면 쉽게 이제 좀 준비를 했습니다. 네. 그래서 이제 액정이라고 하면 리퀴드 크리스탈. 이게 영어로 강의해야죠. 혹시 외국인, 네네네. So I'm going to discuss about liquid crystals. So here is the title. This is the overview of my talk. First of all, I will give just a brief introduction of what is a liquid crystal, and then I will spend just a little minute to explain the classical theory of liquid crystals, and then somehow there's some difficulties to describe general liquid crystals using classical ocean Frank energy. And recently, we are interested in Landau-Juzang theory. You probably know that both people, Landau and Juzang, and they contribute in physics a lot. So finally, I will give some interface problems between two different phases. So here, everybody, I think you haven't heard liquid crystal many times on newspapers, in TVs. What is a liquid crystal? Liquid crystal is intermediate state of matter between liquid and solid. So one of a famous example for liquid crystal is a soap bubble. So when you take shower, when you make a bubble is actually liquid crystal phase. And that's the first thing, one of a popular example. And then liquid crystal has the properties of both liquid and solid. Liquid and solid. And so therefore, it has both properties of liquid and solid. So the structure of systems of liquid crystal is very complex because it flows like a liquid, also has some orientational order. And one of the famous example for liquid crystal is to make displays, also optical switches. The picture I showed here, so I got a couple of years ago, and this one is one from homepage of UPenn, University of Pennsylvania, and they have in physics department, they have very strong group of liquid crystals. And this is actually a picture of insect eyes. So when insect eyes, and then inside the eyes, they call it a colloid. So there's some colloid inside, and then there is some liquid crystal faces. It looks like sphere, looks like small, big sphere, and then when you go to the boundary, smaller and smaller. So this is one of the liquid crystal faces. So using this picture, actually UPenn group, groups in UPenn, they they actually try to produce this kind of structures using liquid crystal. So, yes, okay. They actually produce this type of structures using some materials in liquid crystals. So here are the most useful application of liquid crystals. You have you have cell phones, laptop screens, and then some displays. Okay. And recently also I attended some chemistry workshops, and so actually these are the face of liquid crystal. This is a liquid crystal, and then they actually make the sphere-like shape, and they put some polymer on the boundary. So it actually, when you have a polymer fixes boundary conditions. Okay, that's the boundary conditions, and molecules aligned perpendicular to the boundary, and when you move this around, this actually catch the breast cancer cells. So they try to use this technique to detect cancer cells. Okay, so then so there are many phases in liquid crystal, and one of the basic phase is this one. So when you look at the in the middle, when you look at the one point, and the molecules has no preferred directions. It's like isotropic fluid, so there's no preferred directions. So which means when you look at the direction of molecules are random. So which means when you take one point, and then you look at the small region here, and then you look at the compute the average directions of molecules, it becomes 0. So there's no preferred directions. But when you lower a temperature from isotropic phase, a molecule try to align in certain directions. So this is locally. And then in order to study the direction of this structure of molecules, we are interested in only direction of molecules. When we denote one point direction, at each point you look at the direction field n, and magnitude equals 1. And this is we call it, this is a nematic phase. So in this case, we consider molecules are all rod-like molecules, so which means uniaxial. You look at it like sticks. Yeah. So the energy, the governing energy for this kind of liquid system is famous one is Ocean-Frank energy. Ocean is also, he suggested the energy in 1936. But somehow between in 1940s or something, scientists thought the liquid crystal we don't need to study further because it's all not many liquid crystals exist. But somehow in '56, and Frank he actually recalculated this energy, and now we put the Ocean-Frank energy for liquid crystals, and the energy looks like this one. I'm not going to spend the time for this energy. This one energy was well studied during the 1980s and 90s. Yeah. So here the n is a unit vector from omega to S2 unit vector, and then you minimize this energy subject to these conditions. So this is one of our typical problems. Yeah. So the one of the basic important work for this one is the existence and partial regularity of this energy is done by Bob Hart and Kindlerer and Fang-Hwa Lin. So this is and then there are many energies work studied by this energy in, I already told you, the 1980s and 90s. But one of the famous one is when these all constant K1, K2, K3 are the same, then the energy reduces to this one. And then when n is minimized of this one, it satisfies this equation. So this is a harmonic map. Yeah. And then what's known is that this one, it was proved by Richard Schoen and Uhlenbeck in 1983. And if n is minimized of this energy, then n is held continuous except finite point. Yeah. This is some work related to this work, but I'm going to pass this one. And this one is when the Ocean-Frank energy has a minimizer, has a singular point, and singular point look like this one. This is the real picture. It's not a computational picture. This is a real picture. And this is one singular point. Yeah, this is a singular point. And then when you understand the behavior of these molecules around this singular point, and the singular point is really looks like, if this is point x0, singular point looks like x minus x0 divided by its norm. Yeah. And then you rotation, and using the rotations. That was proved by Uhlenbeck and Richard Soens. Yeah. So this kind of singular point happens only for this Auchen-Frank energy. So only when Auchen-Frank energy minimize of this one allows a singular point should look like this one. Yeah. Yeah. But in physics literature, it has been observed that what happened is that, so this is the sort of a cartoon picture for singular point. So singular point here, so this is kind of singular point. And then what happened is that, when you look at we look at the small circle around this point, and then suppose the molecule points these directions, and you follow the path, and then when you go up, this rotate by 90 degrees, and then you follow this curve again here, and actually point these directions. So actually, when you look at the direction of molecules along this curve, then it rotated only 180 degrees instead of 2 pi. It rotated only pi. So then what happened along this line? This side, all molecules point these directions, and opposite side, all molecules opposite directions. So when you look at along this line, when you compute the energy of Auchen-Frank, it becomes infinity. So which means this type of singular points does not appear in the Auchen-Frank energy. So we need more theory to describe this kind of situations. So that's why we need the more general theory for liquid crystals. So that is Auchen-Frank and this Landau-Zhang theories. So from here, I'm going to stop here, and I'm going to use Blackboard from now on. Yes. Because the equation for liquid crystal is very complicated, so when I presented many times, but people think it is very complex and it's hard to understand. So I try to use Blackboard to give some basic theories. Okay, so suppose we have one domain. This is omega, in general in R3, on domain, and suppose one point x. I want to know if we describe direction of molecules. So there's direction of molecules. So how many possibilities do we have here? S2 possibilities, right? So given point 4, x in omega, then let rho. So fixed point is this given x, and rho is omega or S2 to R positive plus or be a probability distribution function molecular directions, so one given point. And then probability density satisfies the integral for integral over S2 rho d. In general, we say P vector dP equals to 1. And also, the molecule has no head and tails. So then this one has satisfied the symmetric conditions. Rho minus P equals rho P for rho for every P is in S2. So this is the distribution function for molecular directions. And also, you can also assume they're continuous. Easy way is to compute the continuous. Yeah. And then when you have the directions, and then when you look at the first moment of this distribution function. So let's look at the first moment. First moment is nothing, just the integral. P rho P. I think M dm. Okay. This dm means the surface measure on S2. Okay. So when you compute this one, this becomes 0 because of this symmetric properties. These symmetric properties, when you look at the half sphere and the upper hemisphere and the lower hemisphere, the integral becomes minus sign, becomes 0. So first, using the first moment, we have nothing to use. And I compute the second moment. Second moment. So second moment is defined to be over S2 M tensor M rho M Tm. So this is the second moment. So this is the second moment. So here I'm using notation V W A. This one just V I W J. I from 1 3, J from 1 3. This is the second moment. Yeah. This is the definition of second moment. And then when you look at first case, if rho m equals to 1 over 4 pi, suppose you have the rho is a constant function. So all possible direction has the same distribution, which means isotropic. So this is for isotropic fluid case. And then when you compute the second moment, for this case, there's 1 over 4 pi, m tensor m, and dm. So this would be, I think, when you compute 1/3 identity matrix, so you can actually compute. So for isotropic case, you have a 1/3 identity matrix, and this is the second moment for this type of this liquid crystal. And then we define the Q is a matrix. It's the given. So here I didn't write down X, but given X point, and then I have a Q matrix, and this one is defined to be S2 second moment. So M rho M dm minus 1/3 identity. So this is actually measures the second moment, how the molecules deviate from the isotropic phase. Yeah. So this is the definition of Q. And this is actually 3x3 matrix. Yeah, this is a 3x3 matrix. When you compute a trace of this matrix, it becomes 0. So trace means you have a 3x3 matrix, and you look at the diagonal. Sum of diagonal becomes 0. And then obviously you can see that Q is a symmetry matrix. Yeah. is symmetry matrix. And then we are going to use this the matrix Q to describe liquid crystals, molecules. And then you can compute the eigenvalues and eigenvectors of this one. And when you have this, you can write down Q in terms of lambda 1 and so these three eigenvalues are perpendicular to each other. That would be the same. You have three eigenvalues. Then you got eigenvectors and double like this one. So this lambda 1, lambda 2, two eigenvalues. And then W is actually N cross M. Yeah. And this these are eigenvectors. Yeah. In this way. And then from here you can actually look at the here's a remark. So I'm not going to calculate all of them, and you can easily check that if lambda is an eigenvalue of Q, by definition this is the Q, then lambda should be between minus 1/3 and then 2/3. So should be belongs to this range. All eigenvalues should be in here. Yeah. And then what happens if lambda equals minus 1/3? So just to check the what if lambda, one of the eigenvalues becomes minus 1/3. So if lambda, okay. So I'm not going to check that one. So only look at this one. This is the lambda should be between minus 1/3 and 2/3. Yeah. So these are the basic ingredient to describe liquid crystals. And then here's the definition. So if a liquid crystal is uniaxial. Uniaxial means this is defined by optics. So optics are uniaxial. If two eigenvalues equal. Yeah. When two eigenvalues are equal. So if two eigenvalues are equal, then you know, suppose lambda 1, lambda 2 are the same, lambda 3 are different. Then when you look at the this is the n1, this eigenvector. Suppose eigenvector, this is the m. Another eigenvector. Corresponding eigenvalue is lambda 2. This is lambda 2. Lambda 3 different. So we have another eigenvector, this one. And then when you look at the distance, this is the absolute value is lambda 2. These two are, the lengths are the same because lambda 1, lambda 2 the same. And then when you look at, then you make ellipsoid like this one. And this is rotational symmetric along this axis. So this actually looks like a stick. So that's why we call this uniaxial. The molecules look like this way. So this is rather like molecules. That's why and in optics, there's only one axis for optics. So that's why it's called uniaxial. And then a liquid crystal is biaxial. Biaxial means if all three eigenvalues are different. All different. This is which means when you have this is lambda 1, the length is lambda 1, this is the length is lambda 2. These three are all different. So which means when you have this is not rotational symmetric. So rotational symmetry is broken. Yeah. This is a biaxial region. Yeah. And then the governing equation, and then the governing equation, energy functional. So let's call E Q. So the energy depends on Q. The governing energy EQ is the integral over omega. So omega is domain in R3. And then we have some L1 and Q, Ij. Let me use the same notation. Okay. Let's see. The governing equation, let me write down in this way. So F Q and then gradient of Q dx. So this is the governing equation. And then this energy in general, F satisfies this. Yeah. First condition, F and Q and gradient Q equals, and then this is when you compute the energy should satisfy frame indifference. The frame indifference means when you change the basis, on the basis, then energy should be the same. Yeah. So which means this is the same as F R Q R transpose, and then some D star. So here where D star is 3 by Dij K equals to, this is third order tensor. This is the third order tensor. This is a little bit complicated, but Ji, Jl, R, Jm, R, Kp, Q, Lmp. IL, Jm, Kp, QLp. Yeah. For every Q is in O3. Okay. This is just the frame indifference. So just change, the energy is invariant under basis, change of basis. And then you compute, and then using the symmetric structures, you compute the energy. Yeah. You could. So first you consider the energy is polynomial in Q, polynomial in gradient of Q, and then you compare all the coefficients somehow, and then you got some coefficient has some relations, and then you put all chunk together. You end up with getting then F Q and gradient Q. You can write down in two parts. So one part is Fe, elastic energy. F elastic energy and the F bulk energy, we call it. And simply this one, F elastic energy, it should look like this one, L1, Q, Ij, Ijj, Q, Ik. Let me write it in this way. Divergence of Q, and then L2, curl of Q, and then L3, gradient of Q. squared. Yeah. And then we have in general another form, L4, that would be Q, this is a little bit complicated, Q, LK, Q, IJ, and L, Q, IJ, K. So where Q, IJ, K means you differentiate Q, IJ with respect to XK. So comma K means you differentiate the respect to XK. So this is the energy, elastic energy. So here definition of divergence of matrix is this one. So you have a
So here, what do you mean with the exothermic tensor? Exothermic tensor.
You mean?
What is the precise?
You mean this one?
Yeah.
Ah, there's a component. You have each component you squared and square root.
Okay.
Yeah.
Yeah, Euclidean.
Yeah, Euclidean norm. Yes. So here divergence means you have Q11, Q12, Q13. Divergence Q means you take this as one vector. Yes, divergence of first vector. Okay, divergence Q11 difference with respect to 1 and plus Q12 with respect to 2, Q13 with respect to 3. So, and this actually got vector. So this is the vector. Yeah. Here curl means you consider this one vector and they compute the curl of this vector. So, and they have 3 components. So that's why I have this one. Yeah. And then F bulk energy is this one. F bulk is in general 2, this is 2 Y0. This is certain temperature, T minus T star. And then trace Q squared. Yeah, trace Q squared. And then minus 1/3 B. This is trace Q cubed. Yeah. And then C over 4, this is trace Q squared N squared. Yeah. So this is nothing but, this is just the Q has eigenvalues, right? Q has 3 eigenvalues. This is the same as the summation of lambda I squared, I from 1 to 3. Yeah. So eigenvalue squared. Yeah. And then this eigenvalue squared. And then this is somehow is the same. Okay. Yeah. So this is the bulkhead. We call it bulkhead. This is kind of what you can consider the potential energies. And then this is some certain critical temperature. When you change the temperature, then this could be positive and negative. It gives the phase transitions. Yeah. This is the basic energy for liquid crystals. Yeah. So this energy is called the Landau-Dujang energy. So this energy, this one is called the Landau-Dujang energies. So Dujang, actually he is the recipient of field medal. Is one of the reason is the contribution to liquid crystals and superconductors. Yeah. And then we have the U minimize now in mathematics. We minimize this energy, this F Q and gradient Q dx subject to trace Q equals 0 and Q is symmetric. And we have some constraint like this one. So whenever we have a constraint, it brings, when you minimize certain energy with certain conditions, it brings Lagrange multipliers. So computer Lagrange multipliers is more difficult work. Oh, we have some, yeah, also some boundary conditions. Yeah. Some boundary conditions. And then why we use this Q instead of N? So here's a remark. So one of the reasons I was interested in this Landau-Dujang energy is to study the singularities I already showed in the picture. So here I showed a bit before, it's some 1 point, and then molecules n direction, this direction, n is along this curve, and the direction of n is this one, like this. And then when you come back to here, it's actually the opposite directions. And then along this line, n jumps from this direction to opposite directions. Okay. Suppose this is small, this is L. When you compute the integral, you compute the energy around, along this curve. This becomes infinity for these cases. Yeah. Because n is discontinuous, it jumps from here to here. So energy goes to infinity. So this type of this singular point A cannot be minimized over this type of energy because this energy has infinity, blows up infinity. But if you use Q, so one of the simplest Q is this one. Suppose you have N, Q looks like this one. So when your Q looks like this, S M vector, N is in S2. Yeah. And when you compute the eigenvalues, this one, eigenvalue of two eigenvalues are equal. So this has equal two eigenvalues. Two eigenvalues are equal. When you use Q for these situations, so although when you use n jumps from here to here, opposite directions, but Q remains exact the same, right? So when you replace n by minus n from here, this one is all the same. So using Q, this is actually smooth along this line, along this curve. But when you use n, it jumps. And then you look at the energy, it's infinity somehow. But when you use Q, never change along this line. But Q has a finite energy. So Q has more possibilities than using the n. That's the reason why we are interested in Q instead of n. Basically,
so Landau energy is just a generalization of the Ocean-Frank?
Yes, that's actually generalized generalization of Ocean-Frank. Yes, yeah. And then this is much better. Here, when we model molecules, the molecule has no head and tail. N and opposite N is the same. We have to work on the RP2 instead of S2. So basically, Q is actually, corresponding to, this Q is corresponding to element in RP2. Yeah. So Landau-Dujang energy actually working on, so Landau-Dujang energy, using Landau-Dujang energy. We are not using the RP2, but somehow Landau-Dujang energy uses, we work on RP2. This is the original model for molecules. Molecules has no head and tail. So when you look at all space satisfying this one, these conditions, this is actually working on RP2. Yeah.
So then, is it possible to use in the RP2 space calculate the first movement to give any?
Oh, you mean this one?
Yeah, first, because if we use RP2 space for the first moment, it will.
Then it is non-zero.
Yes. So does it give any good information?
I don't know. I never thought about it. That's a good question.
Yeah. We keep using the second moment, but first moment.
Yeah, and then but when you use when you compute that one, then you wanna work on the Ocean-Frank energy instead of Landau-Dujang energies, right? So Ocean-Frank energies, you use RP2, you have to lifting. You have to use something lifting lemma and some other stuff. Yeah. And then one of the thing I want to remark for Ocean-Frank energy, when at the beginning I defined the Q. So at the beginning I defined the Q, eigenvalues of Q should be between -1/3 and 2/3. Okay, but when you have energy, there's no constraint for eigenvalues, right? Okay, so when you minimize this energy, we don't know whether the eigenvalues of this one is greater than 2/3 or less than -1/3 somehow. So that is a little bit defect for Ocean-Frank and Landau-Dujang energies. So, but the Landau-Dujang energy does not contain constraint for eigenvalues. So this is one of the things we have to fix, Landau-Dujang energies. And then, because of this one, and actually the work by Jambo and Appala Majumdar, so Appala Majumdar was at the time postdoctor of Jambo. They actually fixes this energy. By adding the certain energies, integral omega rho ln rho minus kappa and trace q squared, something like this way. So instead of using F bulk energy, they replace this energy by this one. Energy by this one, and the role of this energy, the role log rho, makes the molecules to be disordered state, and then this one has ordered state. Disordered state, they compete each other. Yeah. Yeah, this is entropy energies. Yes. So you can look at the Ball and Majumdar's paper, and then they actually prove some existence of minimizers in certain class of functions, and then they have work. They fix this one, and then somehow there's another group of working this type of equation is the Peking group. So in general, Ping-Wang Zhang. So Ping-Wang Zhang's group actually they try to understand Landau-Dujang energy, and then Ocean-Frank energy, and then this density functional theory, DFT. We call DFT. They look at all the connections somehow. So they actually have the same type of energy. So they use some different modeling. They're using density DF density functional theory, somehow DFT, using this one. And they actually, in some cases, they match the same. So they get the same type of energy. The energy look like, so let me, I cannot see the time. 10분 남았어요. 네. Yeah. So actually we have, I'm going to using different. Yeah. And actually this is also the same as, this energy is actually the same as omega, and then somehow Q, and then B Q minus log GQ minus kappa gradient Q squared. So what I mean by BQ is Bingham closure. So in Bingham closure. So B actually look like this one. Whenever Q is given, you can find matrix 3x3 matrix B satisfying the following equations. So this one. So whenever matrix Q is given, I can always find integral over S2, and this one exponential function, and the matrix B Q, and then M tensor M. So this is 3x3 matrix, this is 3x3 matrix, and then inner product between matrices. You multiply component and then sum them up. So you got this one, and then T M. And then integral over S2, and this is M tensor M minus 1/3 I exponential BQ X BQ M. So whenever Q is given, you can always find the 3x3 matrix B satisfy these equations. And then you put this one in the energy, and you minimize this one with the elastic energies. So this energy is exactly the same as this one. Yeah. So this is the Jumbo's group, and this one is Ping Zhang's group. They actually agree with each other. So basically, remark is that yeah. So here's one remark. And then this energy, so for Q is really nearby the zero matrix. Okay, this is zero matrix. This is isotropic zero matrix. So zero means Q equals zero means isotropic. It's isotropic. So in the phase transition from isotropic to liquid crystal, near the phase transition, and this energy star, this is star, is you can write down kind of using Taylor expansion. This would be A over 2 trace Q squared 1 B over 3 trace Q cubed, and then C over 4 trace Q squared, and then you have higher order terms. Okay. So when you study the Landau-Zhang theories near phase transition to isotropic to liquid crystal, using this energy is enough. So Landau-Zhang energy is actually enough to study phase transition from isotropic and liquid crystal. Okay, I think I have only 5 minutes left. Okay. So I'm using too many times to explain this one. And then the last part, I just give just brief mention what is the interface problems. So here, I was interested in interface problems between isotropic nematic liquid crystal. Nematic phases. So what, and in that case, we don't want to use this, this complicated energy functional. This is very complicated. But as I explained, near the phase transition from isotropic and liquid crystal, that is enough. This one is enough. And so with the so these are the Peking University. He was in Zhejiang University. So with joint work with these people, we studied interface. Or what kind of problem is that you have a domain. So you have a 2D. Suppose you have 2D domains, and then in general, in the isotropic and liquid crystal phase, they mix each other. So now we are interested in this is isotropic. Suppose this is isotropic, and this is the liquid. This is nematic liquid crystal. Nematic liquid crystal, and the isotropic means Q equals 0 in this domain, and then here liquid crystal. There around here, we are interested in only this part. Okay, only this part. And here, suppose you have molecules point in certain directions, and then we are interested in the profile between Q equals 0 to this state. Okay, and then suppose this is a very small epsilon region. When we scaled, epsilon goes to 0, and then you have a rescaled. You have been rescaled, and then somehow you can actually give boundary conditions. This is called the minus infinity equals 0. Q plus infinity becomes this one is S n cross n minus 1/3 identity matrix. So this is actually the interface between isotropic and nematic. This is a nematic phase, and then when you look at certain values. And then the simplest problem is the 1D problem. This is still a very complicated problem. For 1D problems, we proved for 1D, so for this one, it's better to use slide, but at times. For 1D problems, this is infinity, here is minus infinity. And then what happened is this is a Q equals 0 at minus infinity, Q equals 0, plus infinity, Q equals to n tensor. This one, this is a Q0, and this is Q0, plus infinity. And then we are interested in the profile between minus infinity plus infinity. And then we proved a certain region here. And here is all eigenvalues, 2 eigenvalues equal around here. This region, 2 eigenvalues equal. And certain region, 3 eigenvalues are distinct. They have all distinct eigenvalues. Yeah, that's the one of the thing we proved. So this one appears in calculus variations and PDEs. Yeah. And then in this paper, we pose many open questions in the papers. So there, if I have more times, I can explain more problems. But I think you already have a time job, so it's better to stop here. Thank you for your attention.